Hello, my name is Shashank Shekhar, and in today's class we will be learning the third chapter of class 11 chemistry, that is the classification of elements and periodicity in properties. So you have studied about the periodic table in the earlier classes and about the periodic and modern periodic law. Now we will see how this periodic table help in predicting the physical and chemical properties of elements and how does this trend happen. So what is trend? So suppose you are moving from down up to down, then how is the melting point changes, the freezing point is changing. So these are the things we will see, that how this trends happen in the physical properties and the different properties of element. So first we will see about the physical properties. Okay. So for that we will consider the first physical property, which is the atomic radii. Okay. So what is atomic radii? So if I give a brief content about it. So suppose this is the outermost shell of an atom. Okay. And this is our center. Okay. Now, if we measure the distance between this center and the outermost shell, then we call this length as r. So this r will be called as our atomic radii. Okay. So the parameter of this atomic radii is too small. It is approximately 1.2 angstrom or 1.2 into 10 to the power minus 10 meter. Sorry, it will be superscripted here. Okay, minus 10 meter in radius. But the problem is that this length is too small to measure with any instrument with accuracy. Okay, for that thing we take the covalent radius. Okay, so what is covalent radius? So suppose this atom which you have to measure the atomic radii, it is named as A. Then we take a molecule. Suppose we are taking a molecule which is A2. Okay, A2. Okay, so this is atom A, this is atom A1, this is atom A2. Now we measure the distance between the centers. So this is our center of both of this atom. We measure it. So this thing is called the covalent radius. Okay, so suppose it is A. So it is called as covalent radius. Now we take the half of this and consider it at the atomic radius. So for the time being, for the whole of the chapter, this atomic radius only, this specific atomic radius will be considered in all the calculations and all the tables. Okay. So this thing is called the covalent radius. So for metals, it is called as metallic radius. So it is same. Just the name is changed. So if you're taking a covalent molecule, then it is called a covalent radius. And if you're taking a metal, suppose we're taking iron. So these are the two iron atoms. Okay, so this is iron 1, this is iron 2. Okay, these are the centers. If we measure the distance between their centers, then this length is called the metallic radius. And if we take a half of it, then it is called the atomic radius for the metallic metals. Okay, so how do we measure this atomic radius, or the specifically we can say the covalent radius or the metallic radius? We measured it by using the X-ray or some other spectroscopic method. So spectroscopy is nothing but the interaction of light with matter to study the various properties. So it is called spectroscopy, and we use various radiation of various wavelengths to serve our purpose. So X-ray is generally used for this purpose. Many other radiations like the infrared are used, and suppose for a large observation, which for which we require large wavelength, we use our visible thing. Okay, it is quite simple. So for this reason we are taking the X-ray. Okay, now we will see the trend of the atomic radius in the periodic table. So if you look at the periodic table, first of all, so you will see this kind of diagram in it. Okay, I am doing just a rough diagram, not the accurate one. Okay, so if you move from up to down, so we take this column here, and moving from up to down, then we call it as group. You have studied about it, so it is covered in the previous lecture. I am just giving a reminder of that. Okay, and if we move across a row like this, so suppose this is the first row, so we call it as period. Okay, periods. Okay, now how this atomic radii, what is the trend for atomic radii for this group and periods? Okay, so if we move across a periods, then the atomic radii decreases. So if we move in a period, then the atomic radii decreases. And if we move down the group, then the atomic radii increases. So what is the reason behind it for this increasing and the decreasing nature, or the decreasing trend or the increasing trend? So the first reason that we will see is the effective nuclear charge. So if you're moving across a period, so we're considering a period like carbon, then nitrogen, then oxygen. Okay, so these are the elements of the same period. Okay, so if you move like this, so suppose A is the atomic radii of carbon, B is for nitrogen, C is for oxygen. Okay, so A will be the greatest one, then B, then C. So what is the reason for this trend? So first for that, we have to understand what is effective nuclear charge. Okay, so if you consider an atom here, so I am considering an atom here. This is our nucleus. Okay, and this is our electron. Okay, then this nucleus will apply some force on this electron. Okay, so the force, that the net force that is experienced by this electron from this nucleus is called the effective nuclear charge. Okay, so in simpler terms you can say that. So when we move across a period, then we get on adding electron to this outermost shell. Okay, from carbon to nitrogen to oxygen. So its atomic number is 6, it's 7, it is 8. So we are adding electron to this outermost shell. So what does happen? What happens due to this? So suppose the electric force, or the electrostatic force in particular, you can say, that is experienced by this shell goes on increasing. As you know that the electrostatic force is directly proportional to the magnitude of the product of the charges. Okay, so if we keep on increasing this charge, so it is increasing, so this charge is constant. Suppose it's for nucleus Q1, but for this shell it is increasing due to increasing number of electrons. So this shell will experience more and more force. Okay, so to stabilize that force, it will move in the inward fashion. Resulting in a decreased atomic radius. So this atomic radius decreases. Okay, writing it clearly here. Atomic radius decreases. Okay, so this was the reason for the decrease in the period. Now we'll move to group. Okay, for group, if you consider for group here, okay, so this is a graph. If you see it here, this is a plot of atomic radius versus the atomic number for a period. This is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So if you see here, it is approximately 150 unit, or for this it is picometer, it is mentioned here. So 150 picometer. Okay, so this is approximately 110 picometer. So we can see there is a decreasing trend in it, and I have told the reason. The reason is same here, because it is a period, because the number of electron in the outermost shell is going on increasing. Okay, it is increasing as we move across a period, and due to which we the outermost shell experience a large effective nuclear charge, and it contracts to balance that. So the atomic radii is decreased as the result of it. Okay, now if we consider a group, so this is a group we are moving from lithium to sodium to potassium, then rubidium, then cesium. So we are seeing that atomic radius is increasing across a group. So why is it so? So the reason is very simple for that. So for lithium, there are two shells. Okay, first shell and the second shell. Okay, but if we look at sodium, so suppose this is the sodium. So there are three shells for it. 1, 2, 3. Similarly, if you move to potassium, there are 4 shells. 1, 2, 3, then 4. So you can see clearly that due to the increase in number of shells, the atomic radius is increasing. So this length is increasing as we move across down a group. Okay. So it is obvious support digit A, so it is B, and it is C. This is lithium, and this is sodium, this is potassium. Okay. Now, we will move to another thing that is called the ionic radius. Okay. So what is ionic radius? So consider an element X. If we move an electron or add an electron, both, then the atom or the element, which is what was initially electroneutral, it is disbalanced in terms of charges, and it becomes positively or negatively charged. Okay. So suppose that we are adding an electron. Okay. So this is our electron. Then we get a negatively charged species, and it is called as anion. Okay. And it is negatively charged. Now similarly, if we remove an electron from it, we get cation as the ionic species, and it is positively charged. Okay. So we will call it as X minus, then it is called it as X plus. So in this way we can get our anion or cation, which are ions, and this one is called, this is negatively charged and this is positively charged. So what happens if we remove the electron from it, or if we add the electron to it? So in case of removal of electron, the size is decreased, means the cation size is smaller as compared to the parent atom. So this is our parent atom X. So the radius of X will be greater than the radius of X plus. Okay. So why is it so? Because initially there were large number of electrons. Okay. So suppose it was this. Okay. So it is this. So suppose there are 3 electrons in the outermost shell. Then we have removed 1 electron. Okay, minus 1 electron. Then they get this species here. It has 2 electrons. Okay. So while the number of electrons have been reduced, the positive charge at the center is not getting affected. Okay, it is clear because we are not removing any proton. So the net charge field by this electron, means the electron which are being attracted are getting more force of attraction as compared to these 3. Okay, it is quite simple. So initially, suppose 3 protons were attracting 3 electrons. Now 3 protons are attracting 2 electrons. So due to this, they will experience more force and they will move inward. Okay, this shell will move inward and resulting in a decreased radii. Okay. Now, next, if we move to anion, which is negatively charged, so we are adding an electron plus electron to get our X minus. So what happens? What does happen? So suppose this is our, so it has suppose 3 electrons. Okay. Now we are adding 1 electron to it. So what will happen? It has initially 2 electrons. Now it is 3 electrons. The first thing it will happen that this electron will now experience less effective nuclear charge, because less effective force, because the number of protons have been same, but the number of electron is increased, and further there is a repulsion between this electron, increased repulsion. Okay, so there were 2 electrons initially, now they will experience more repulsion. Okay, due to this shell will expand, so that the repulsion could be decreased by increasing the distance between these charges, as we know that electrostatic force is inversely proportional to the distance. So as this electron will move apart from each other, so as to reduce the effective repulsion force, this will have a greater radii as compared to the parent atom. So X will have a less radii than the X negative. Is this thing is clear? Okay. So we have seen two or more things here. So one more thing is here. It is mentioned here about isoelectronic species. Okay, it is an important concept. So what are isoelectronic species? So these are those species or elements or ions, you can say, which have the same number of electrons. Okay, so suppose our atom is carbon, your second atom is nitrogen. So carbon has 6 electrons, nitrogen has 7 electrons. If we remove one electron from nitrogen, then we get a species as carbon and nitrogen plus, and this is carbon. Okay, so these two will be called as the isoelectronic species. Similarly, if we remove 2 electrons from it, from oxygen, then we will get O2 plus. So these three will be called as the isoelectronic species. Okay. Now, next. Okay, so the cation with a greater positive charge will have a smaller radii. So it is obvious. So suppose you have a parent atom as X, then you have a X plus, then you have X2 plus. You are removing electron consecutively. So remove one electron, you get X plus. You have removed one more electron, you have got X2 plus. So what will happen? So the reason is quite simple, that it will have a reduced atomic radii consecutively because the effective nuclear charge is decreasing as we move from left to right in this fashion, while the number of proton is remaining same. So the outer shell will experience the more inward force and it will result in a smaller radii. So suppose it is A, this is B, this is C. So A will be the largest, B will be the larger than C, and C will be the smallest one. Okay. Similarly, for the anion, if we have 3 elements whose radii are X, X minus, X2 minus, radii are A, B and C, then C will have the greatest radii, B will have the smaller than C, and A will be the smallest one. Okay, the reason is quite simple, because we are adding one electron, due to which there is reduced effective nuclear charge and increased repulsion among the electrons. Okay. Now, you have seen in the atomic radii case that we are adding electron and removing electron. Okay. So first we will consider the removal of electron. So if we remove an electron from a neutral species or from a charged species also, then we will need some force to do so. Okay. So some energy should be spent on doing so, and that energy which is spent on moving an electron is called as ionization enthalpy. Okay, so this is just a quantitative measure. So it is a measure of quantitative measure of how much energy is required to remove an electron from a species. Okay, and specifically we can call it as isolated gaseous atom. So why is it so, and how is it so? So suppose we have a compound that is X2. To calculate the ionization enthalpy, first we have to break the bond between the 2X atom. Okay, so this is XX single bond. So we will get 2 of X, means 2 atoms of X. Now we will take one atom of X, and it should be gaseous. Yes, it should be gaseous. So initially it was gaseous only. Suppose we are taking the gaseous form of X2. We are taking like nitrogen gas or the carbon gas. So we will get as X gaseous. Then we will remove -1 electron from here. Okay. So we'll get a charge, positively charged species. Okay. So the energy required from this to this, okay, from this to this, the energy spent from making this isolated gaseous X atom to isolated gaseous X plus atom, or the X plus ion, is called as ionization enthalpy. Ionization enthalpy. Okay. So some energy must have been spent here, plus delta H. I am representing it plus delta H. Okay. Now, so in this thing, something is called as it as first ionization enthalpy. So if we are removing the first electron, then we call it as first ionization enthalpy. Suppose this is our isolated gaseous atom X. We are removing one electron. Okay, we are getting X plus gaseous. So this removal of first electron is called the first ionization enthalpy. Okay. and its unit is kilojoule per mole. So it is generally represented as kilojoule per mole. One very important thing, means I am saying it every time, that we will spend some energy in doing so. So you can't just do it by applying energy. Means energy will never be released from this process. So it is a kind of endothermic process. It is a endothermic process. So you will study about this endothermic process and the exothermic process in the thermodynamics. So I'm giving a brief gist of it here. That's what is endothermic process. So any process which require giving of energy, means it takes some energy is spent in it. Then that process is called the endothermic, while the process which has tendency to release energy is called the exothermic process. Okay. In that series only, the second ionization enthalpy, or the energy that is required to move the second electron, is called the second ionization enthalpy. So it is quite simple. So suppose we are moving from X gaseous to X plus gaseous. Then we are removing one more electron to get X2 plus. So the energy which is required from going from this to this, okay, is called it as second ionization enthalpy. Now one thing I should make it clear here. So suppose I am representing the first ionization enthalpy by IE1. Okay. And the second ionization enthalpy is IE2. So one thing should be always kept in mind, that it is an important thing, that ionization enthalpy 2 is always greater than ionization enthalpy 1. Why is it so? So suppose you are removing an electron from a neutral species here. Okay, so I mentioned it here also. So you remove an electron from the neutral species here. So it will require less amount of energy. Okay, so because it is a neutral species, it has the same number of electron and same number of proton. Means proton and electron count are same. But when we are doing the second ionization enthalpy, when we are removing the second electron, then the number of proton is already high. Okay, so it is a charged species, a positively charged species specifically. So already the outermost electron is experiencing greater force as compared to this neutral atom. So we have to spend more energy to move this electron to get our X2 species. Okay. So we can say it that ionization energy first is less than the ionization energy second. Okay. Now, this is just a general perception. Okay. So anyone who is saying that, suppose anywhere it is written that ionization enthalpy of carbon is some x kilojoule more or y kilojoule per mole. So by saying just ionization enthalpy, it always mean it is first ionization enthalpy. Unless and until it is mentioned that it is second ionization enthalpy, then we will take first ionization enthalpy as granted for this term also. So it is a general perception. Okay. One thing important, that the ionization enthalpy is related to this atomic radii. And how is it so? So we can see it in the trend, in the periodic trend. We can see that thing in the trend. Okay. So if you remember from the previous slide, that on moving in this fashion across the period, the atomic radii decreases. Okay. I am representing atomic radii from R, so it decreases. And if we move down a group, okay, then the atomic radii increases. So how it will affect this? How it will affect this ionization enthalpy? It is simple. Because as the radii is getting decreased, so during an ionization we are removing the outermost electron. Okay, outermost electron. So as this radius is getting reduced, this electron will experience more force. Okay, experience more force. Okay, due to the decreased atomic radii, and hence we have to apply greater force to move this electron across a period. Means if you move from there to there, the atomic radii will decrease, but the ionization enthalpy will increase simultaneously due to decreased atomic radii. So this and this are closely related. Similarly, as we move down a group, the ionization enthalpy decreases. So it is simple, because the radii is getting increased. So the radii is getting increased. The electron is experiencing less effective nuclear charge, and we will require less amount of energy to remove the electron. So this same thing is mentioned here. So one important term we are seeing here, new term is here, that is called a shielding effect. Okay. So what is shielding effect? So if you consider an electron X, this is the positive charge here, the nucleus is here. So this shell and this shell both are experiencing electrostatic force of attraction from this nucleus. But one thing is unique here about this outer shell, that it is experiencing less force as compared to the inward shell, although it will have the same electron. Suppose it is at 2 electron, it will also have 2 electron. Okay, although having the same number of electrons, this will experience less force. Why is it so? As compared to the original one, means I am considering the distance also, and if we calculate the electrostatic force, then we will get the actual distance of force of attraction, and the measured force of attraction will be different. Means the experimental and the calculated will vary. And why is it so? Because this inner shell here, okay, this inner shell here will shield this outermost shell, okay, from the nucleus and decrease the force of attraction between these two. Okay, now what happened? Due to this shielding effect, this will experience less electrostatic force. Okay, so but as we move across a period, okay, then this nuclear charge outweighs this shielding effect. Okay, why is it so? Because the number of electron is increasing. Okay, so this is the thing. So as the number of electron is increased, this shielding effect is getting reduced because the force of attraction is getting increased due to increased number of electrons. Okay, now for down a group, the reason is simple, that as we move down a group, the number of shell is increasing and the electron are moving further away from the nucleus. Due to this, they are experiencing more shielding effect, and due to this, they are easily removed from the outermost shell as compared to the previous group atom or element. Okay, so this is the trend in the ionization enthalpy. Now there are some exceptions in it also. Okay, so you can see here, so you have seen from the graph that as we move from lithium to beryllium to boron to carbon, there is an decreased radii. So the ionization enthalpy must have also been decreased in the similar fashion, but it increased in the similar fashion, but it is not so. Okay, so the atomic radii is decreasing, then the ionization enthalpy must have increased. But this trend is not so obvious. So if we move from lithium to beryllium, there is an increase in ionization enthalpy. Okay, it is okay. But as we move from beryllium to boron, it is not so. Okay. And why is it so? The answer is, we will get this answer from the shielding effect. Okay. So if we write the electronic configuration of both of this, okay, so I am drawing 2 atomic orbital for it. First is of beryllium, second is of boron. So this is the thing. So there is 1 electron. Okay, so what does happen? So if we are removing this electron, okay, so it will have less shielding effect. Why is it so? Because the 2s atomic orbital are more penetrated toward the nucleus as compared to the electron which is in the 2p. Okay, so this is 2p. So if we consider the atom, then the 2s orbital is more penetrated toward the nucleus, due to which it will experience less shielding effect. So it is obvious. So shielding effect increases as the distance between the nucleus and the electron increases, okay, or the shell increases. But because the 2s electron is more penetrated towards the nucleus, it will experience less shielding effect as considered to this electron which is in the 2p orbital. Okay, so we can draw a general perception from here that s orbital for the same quantum number are penetrated more towards the nucleus as compared to the p orbital. Then you have d, then this is the penetration of the atomic orbitals. Okay, and due to this more penetration of this boron orbital to 2s orbital, it will be much difficult to remove as compared to the boron one. So this is for beryllium. Okay, sorry. For beryllium, it is more difficult to remove as compared to the boron one. And we see this trend. Okay. Now, next exception we can see here from nitrogen to oxygen. So the atomic radius is decreasing, but the ionization enthalpy is not increasing. It is 1402 kilojoule per mole. It is 1314 kilojoule per mole. So it is greater. Okay. This nitrogen one is greater as compared to oxygen. So why is it so? So the answer is behind the electronic configuration. So if you see the outermost electronic configuration of both this, so it is 2s, it is 2p, it is this is for nitrogen, and if you take it for oxygen, it is 2 electrons. So what happened? So if you want to remove this electron, it is easier to remove from oxygen. Why? Because there are 2 electrons in one orbital and there is an increased repulsion between the electron. Whereas while removing an electron from the nitrogen, this is a singly occupied orbital and it is easier to remove this electron from this orbital as compared to this one, which has constituted 2 electrons in it. So due to this increased repulsion, it is easier to remove it, and the ionization enthalpy of oxygen, first ionization enthalpy specifically if we say of oxygen, is less than the first ionization enthalpy of nitrogen. Okay, so this is the reason, means there is 2 electrons in the same orbital, so it is easier to remove due to increased repulsion as compared to the nitrogen, which is in which the outermost electron is singly occupied orbital. Okay, so this is the reason we see this trend here. Okay, so there are 2 exceptions. So first one is beryllium ionization enthalpy is greater than boron, and nitrogen ionization enthalpy is greater than oxygen. Okay, so this is for the second period. Okay, now the next physical property which we will see is the electron gain enthalpy. Okay, electron gain enthalpy. So initially we were removing electron, now we will add electron. So this is the thing we get here. So what we are doing is we are adding electron to a gaseous atom. Here also it is a neutral gaseous atom, isolated neutral gaseous atom, and we are adding one electron to get a negatively charged species which is X minus. And the quantitative measure for that is called the electron gain enthalpy, means the energy which will be spent or released. In this case, it can be exothermic or endothermic. You will see it later. So it can have the energy can have both a negative or positive volume. So the energy required to do so, or the energy which is released in doing so, is called the electron gain enthalpy. The same thing is written here, that depending on the element, the process of adding electron can be endothermic or exothermic. It can release or gain energy. Okay, for many elements the energy is released, so it will depend on the tendency of that atom to gain electron, that whether that atom is accessing the electron easily or it is denying to do so. Okay, so it will depend on that. So if we consider this table here, it is from NCERT. Okay, so you can see that energy is released for halogen atom. Okay, while if we see it from here, so this is for the noble gases, the energy is expended in doing so. Okay, the reason is very obvious. Okay, so suppose you have a fluorine atom, so it is the octet of fluorine is not complete. Okay, it will have a lesser number of electrons than 8. It will have 2 plus 5. 2 plus 5? No. 2 plus 2 plus 5. It will be 9. 9 electrons are there. Okay. 2 plus 2 plus 7. So, this is the electronic confusion of fluorine. So, it is in the 2s. 1s, it's in the 2s. It is 2p. This will have 5. Okay. 5 plus 2, 7. Yeah, it is 5. So if we add one electron to this shell, its octet will be completed. So due to this reason, it will easily accept the electron and complete its octet. So in this process, the energy is released for the group 17 element. It is the halogen are called the group 17 elements. Okay. While in the case of noble gas, they have a large positive value. Why is it so? Because noble gas have already completed their octet, and if we add an electron to it, it will become unstable. So unstable electronic configuration allows for the higher positive value of electron gain enthalpy. Okay. Now electron gain enthalpy have larger negative value towards the upper right of the periodic table. So why is it so? Because when we are adding an electron, so the reason is written here also. So electron gain enthalpy generally become more negative with increase in atomic number across a period. So this is for the group. So if we see in the group, so suppose we are seeing in the group. So when we add an electron to first shell, suppose this is the first shell, this is the nucleus, it is the nucleus. The second shell, we are adding electron to this. Okay. The first shell is more closer to the nucleus. So it is easier to add an electron because this electron which is coming from outside will experience a greater electrostatic force of attraction because the distance is less, and we know that electrostatic force of attraction is inversely proportional to distance. But for this case, the distance is more. So it will be difficult to add the electron. Okay. Because it is experiencing less electrostatic force. So the energy which is released in doing so will be more for this case. Okay. But in the case of period, the thing is different. Why is it so? Because electron gain enthalpy become more negative with increase in the atomic number across a period. This is because the effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron. The reason is similar for here also, that as we are moving across a period, the negative value will increase more and more because the radii is decreasing and the distance between the nucleus and the coming electron is decreasing. So it is easier to add that electron, resulting in a greater negative value of electron gain enthalpy. Okay. So down a group it will decrease. I have discussed it earlier also. So if we move down a group, it will decrease. If we move right side, then it will increase. The negative value, the absolute value will increase, you can say. Increase or decrease. Okay. Okay, now. The next thing is the electron gain enthalpy of oxygen or fluorine is less negative than that of succeeding element. Okay. So if we see the periodic table here, then boron, carbon, nitrogen, oxygen, fluorine. Okay. So oxygen has a less negative value than compared to the succeeding element. So you can see here, this is due to electronegativity. So we will see this electronegativity in the next thing. Okay. So what is electronegativity? So the electronegativity is the qualitative measure. So it is a qualitative measure to accept or take an electron. So what is the difference between the electron gain enthalpy and electronegativity? So electron gain enthalpy is a quantitative measure, while electronegativity is a qualitative measure to accept an electron. It is not a measurable quantity, means it cannot be measured using a instrument. It is just a tendency. Okay. But a numerous number of scales are present for measuring this electronegativity. Means there are some scales which we will use. I mean, we will not measure electronegativity directly using an instrument, but we will take some parameters and then we will calculate the electronegativity of that element. Okay. The electronegativity of an element is not constant. Means you cannot set any trend that yes, it will decrease in this fashion. There is some general trend, but it is not followed strictly, and it varies very abruptly from moving across a period down the group. Okay. But if you take it in general sense, then in moving across a period, it generally increases, and if we move down the group for the periodic table, then it will increase, and the reason it will decrease, and the reason are same as that for the electron gain enthalpy due to the increased radii. Okay. The attraction between the outer shell electron and the nucleus increases as the atomic radii increases. The same reason is written here, that as we move down across a period, the radius goes on decreasing and the distance between the nucleus and the outermost shell goes on decreasing, due to which the coming electron is accepted easily. So the tendency will increase and hence the electronegativity will also increase. So the electronegativity is directly proportional to the metallic property. Okay, so this is a new thing here. So if you move down the group, the metallic property increases. So what do you know about metal? So if you say in a general fashion from our previous study, then we can say that metal is something which has a tendency to lose electron. Okay. So if we move down the group, the electron, the ionization enthalpy is decreasing. You can see there in the trend from the previous slide. So it can the element which can easily lose electron will be a good metal. So this metallic property will also increase down a group. Similarly, if we move across a period, then the ionization enthalpy increases, which result in a decreasing metallic property. So this metallic property is inversely proportional to the electronegativity. Means more an element is electronegative, lesser it will be metallic. Okay. The increase in electronegative across a period is accompanied by an increase in non-metallic character. Same thing written here. And they think these two things are inverse to each other. Similarly, down the group, electronegativity decreases while the metallic property increases. Okay, we will see some points for electronegativity. So first point is that the fluorine is the most electronegative element in whole of the periodic table. Okay, so it is the most electronegative element, while cesium is the least electronegative element. So why is it so? You can say it simply. So it is fluorine. It is the first halogen, and it will easily become a complete octet, and its radii is so small. So two of the reasons are there for its greater electronegativity. First, it will just become stable by accepting one electron, and secondly, it has the smallest radii in all of that halogen, which can become stable by adding one electron. So it is the most electronegative one, while cesium is the most down in the group. Okay, if you see the periodic table, cesium is in the most downward. Okay, so this will have a easier tendency to lose electron, which will result in the least electronegative value. Okay, so this reflects the fact that fluorine is a non-metal. Okay, so you know it already that fluorine is a non-metal, while cesium is a metal with low affinity to electrons. It has a low tendency to accept an electron. So if we summarize our whole lecture of physical properties, you can see here from this picture which I have taken from the NCERT. Okay, so if you move across a period, then electron gain enthalpy will increase, ionization enthalpy will increase, atomic radii will decrease, and electronegativity will increase. Okay, similar for non-metallic and metallic character. So you can stop and see this picture for a bit and get the rough idea about all these properties. So these all things are related to the atomic radii and the effective nuclear charge. If you see it properly, that there is a connection between all of this. Okay, thank you.